The goal of this lesson is to prove Sylow's third theorem, which is the final theorem by Sylow, which plays such an important role in finite group theory. In order to prove Sylow's third theorem, we will use a set called the normalizer. But before we do that, we recall the definition of a normal subgroup. To recall that a subgroup H of G of a group G is called normal if and only if G H G inverse equals H for all G and G. So this tells us that every conjugate of the subgroup H equals H. And this is one way to describe a normal subgroup. Now, we know that not every subgroup is normal. And these are actually a very special type of subgroups. So now just consider a subset of G. It's also not true that given an arbitrary subset of G, if I take the conjugate of that subset, you don't always get the same subset. So this leads to our definition of a normalizer of a subset of a group. So let A be a subset of a group G, not necessarily a subgroup, just a subset. Then the normalizer of A and G is a set of all elements of G that normalize this subset A. So more precisely, this is the set, and we're going to note this by capital N sub G of A. This is the set of all elements in G for which the conjugate of A by G equals A. So we can think of it as the elements G and G for which the conjugate of A still equals A. So this set is always non-empty because, for example, the identity always normalizes any subset or subgroup of a group G. And it actually is a fact that the normalizer of any subset is actually a subgroup of G. Now, let's look at some quick examples of normalizers. If I started out with a normal subgroup of G, then by definition, the conjugate of H is always equal to H for any element in G. So we see that if I take the normalizer of a normal group, that would equal all of G. Every element in G normalizes H. Another quick example. If our set A just contains one element A, then we usually write the normalizer of just the little a, and this is defined as a set of G such that G inverse equals A, but then by multiplying both sides of this equation by G on the right, we see that this is the same as the set of G and G such that GA equals AG. And we know this to be equal to the centralizer of the element A. So it turns out that the normalizer of an element A is the same as the centralizer of that element A. In other words, it's the elements that commute with the element A. And again, the fact that I mentioned earlier, that it turns out for any subset A of G, again, this is not a subgroup necessarily, there's any subset of G, the normalizer of set A and G is a subgroup of G. And it is this important subgroup that will help us count the number of Sylow P subgroups of a group G and will help us prove Sylow's third theorem. So recall the following definition. We stated that the number of Sylow P subgroups of a group G is denoted by n sub p. This equals the number of Sylow P subgroups of a group G. So the following lemma will give us a formula for n sub p, the number of Sylow P subgroups. If capital P is a Sylow P subgroup of G, then the number of Sylow P subgroups of G, n sub p, equals the index of the normalizer of the subgroup P in G. Since these are finite groups, this just equals the order of G divided by the order of the normalizer of subgroup P. And in particular, we see that the number of Sylow P subgroups of group G actually divides the order of G. So our proof begins by defining a bijection T so we will prove this by defining a bijection T from the left cosets of the normalizer of P in G to the conjugates of P and G. And so the definition of this map is T of the left coset X times the normalizer of P is going to equal the conjugate X, P, X inverse. So we claim that this is a bijection to show that T is onto. Well, by the definition of T, this is onto, because if X, P, X inverse is a conjugate of P, then X is an element of G, and therefore X times the normalizer of P is a left coset. So then T of X times the normalizer of P will equal the conjugate X, P, X inverse. So by the definition of T, this is onto. Now to show that it's 1-to-1, let's assume that T of the left coset X times the normalizer of P equals T of Y times the normalizer of P. Then that implies that the conjugate X, P, X inverse equals Y, P, Y inverse. And that implies that Y inverse X, P, X inverse Y equals P, which is the same as Y inverse X, P times the quantity Y inverse X inverse equals P. And this tells us that Y inverse X is in the normalizer of the subgroup P. But if Y inverse X is an element of the normalizer, then that tells us that the left coset X times the normalizer equals the left coset Y times the normalizer of P. And therefore, we see that T is 1-to-1. The inputs must have been the same. So we see that we have defined a bijection T from the set of left cosets of the normalizer to the set of conjugates of P. And so therefore, the number of left cosets of the normalizer must equal the number of conjugates. Well, the number of left cosets of the normalizer is the definition of the index of the normalizer in G. So we see that the number of distinct conjugates of P equals the number of left cosets of the normalizer of P and G, which in turn is equal to the index of the normalizer of P and G. Now, the number of distinct conjugates of P equals the number of Sylow P subgroups of G by Sylow's second theorem. So by Sylow's second theorem, which again tells us that any two Sylow P subgroups are conjugate, we now have that the number of Sylow P subgroups must equal the index of the normalizer of P and G, which equals the order of G divided by the order of the normalizer. And from this equation, we see that the number of Sylow P subgroups divides the order of G. So this lemma gives us a formula for the number of Sylow P subgroups of group G and tells us that this number must divide the order of G. But we can actually know even more information about the number of Sylow P subgroups, and that will be given in the statement of Sylow's third theorem. Let P be a prime and let G be a group of order P to the n times m, where P does not divide M. Then n sub P, the number of Sylow P subgroups of G, satisfies the following. First, n sub P is congruent to 1 mod P. So in other words, the number of Sylow P subgroups is equal to 1 more than a multiple of P. And secondly, the number of Sylow P subgroups divides M, where M comes from the order of the group G, which is P to the n times M. So for our proof, let's let capital P be any Sylow P subgroup of G. We're going to use double cosets of P and P. So let's decompose G into double cosets of P and P. So that is, I can write G as the union over distinct double cosets PX P. So we've already shown that we know how to count the number of elements in a particular double coset. So we know how many elements are in a particular double coset. The order of the double coset PXP equals the order of P times order of P, all divided by the order of P intersect XP x inverse. We're going to break this down into two cases where x is in the normalizer of P and where x is not in the normalizer of P, and we can further simplify this formula for the number of elements in the double coset PXP. Because if we look in the denominator, if x is in the normalizer of P, then xp x inverse just equals P. And if x is not in the normalizer, then this does not equal P. So that's how we'll have a simplification of this formula. So let's look at those two cases. If x is in the normalizer of P, again, that means that xp x inverse just equals P. Then in the denominator, the intersection of P and xp x inverse just equals the intersection of P with itself, which is just P. And hence this double coset PXP would equal the order of P, which is P to the n, times the order of P, which is P to the n, divided by the order of P, which is P to the n, and this just simplifies to P to the n. So whenever x is in the normalizer of P, then the double coset PXP has order P to the n. Now the other possibility is if x is not in the normalizer of P. So if x is not in the normalizer of P, and P intersect x, P x inverse does not equal P. And just as in the proof of Sylow's second theorem, we can conclude that P to the n plus 1 must divide the order of double coset PXP. Again, this follows because P intersect XP x inverse is a subgroup of P, and therefore its order must divide P to the n, but its order can't equal P to the n. So then in the formula, we can deduce that P to the n plus 1 must divide the order of the double coset PXP. So recall that we have written G as the union of these distinct double cosets PXP. Now if we break this down by whether or not x is in the normalizer of P or not, then we can conclude that the order of G equals the sum of the orders of the cosets PXP, where x is in the normalizer of P, plus the sum of the orders of the double cosets where x is not in the normalizer of G, where each sum runs over one element from each double coset. So we're going to simplify these two sums Let's first look at the sum on the left. So note that if x is in the normalizer of P, then the double coset PXP equals, well, I can commute x and p, and so this equals the set p times px, which equals p squared x, but since p is a subgroup, p squared is just equal to p. So we see that the double coset pxp just equals the right coset px. So the first sum equals the sum of the order of px, where again x is an element of the normalizer of P in G, and this runs over the distinct cosets of P in the normalizer of P. These distinct cosets partition the normalizer. So since these cosets partition the normalizer, if you sum up the orders of all these distinct cosets, you just get the order of the normalizer of P. So the first sum just equals the order of the normalizer of P and G. So we have simplified the first sum, and we have the order of G equals the order of the normalizer of P and G, plus the second sum. The second sum of the orders of the distinct cosets PXP, where x is not an element of the normalizer. But recall that we showed that each of these orders in the second sum is divisible by p to the n plus 1. And so since p to the n plus 1 divides each term of the sum, we can conclude that p to the n plus 1 divides this whole sum. So since each term in the remaining sum is divisible by p to the n plus 1, the sum is divisible by p to the n plus 1. Thus, we can replace the second sum by an integer multiple of p to the n plus 1. And we have that the order of G equals the order of the normalizer of P and G plus some integer t times p to the n plus 1. Now we are going to take this resulting equation and divide each term by the order of the normalizer of P. So then the order of G divided by the order of the normalizer of P equals 1 plus TP to the power n plus 1 divided by the order of the normalizer of P. And if you notice that the left-hand side of this equation should look familiar, we just showed that the left-hand side actually equals the index of the normalizer of P, which actually equals the number of Sylow P subgroups, n sub P. The left side equals n sub P, the number of Sylow P subgroups, which is an integer. So, if the left-hand side is an integer, then the right-hand side must be an integer, and therefore the fraction in the sum on the right must be an integer. So therefore T times P to the n plus 1 divided by the order of the normalizer of P must be an integer as well. Now, P to the n plus 1 does not divide the group order G. So since P to the n plus 1 does not divide the order of G, it cannot divide the order of any subgroup of G. So in particular, P to the n plus 1 does not divide the order of the normalizer of P. Again, this follows because the normalizer is a subgroup of G, and Lagrange's theorem states that the order of this normalizer would divide the order of G. And so if P to the n plus 1 divided the order of the normalizer, we would get a contradiction. So the point is that the order of the normalizer cannot contain a factor of P to the n plus 1. And so we can conclude that the order of the normalizer cannot cancel out every factor of P in the numerator of this fraction. So the order of the normalizer cannot cancel out every factor of P in the numerator of T P to the n plus 1 over the order of the normalizer of P. So thus, this fraction is an integer multiple of P. And we have the following. The number of Sylow P subgroups, which we showed equals the order of G divided by the order of the normalizer of a Sylow P subgroup P. And this equals 1 plus T times P to the n plus 1 over the order of the normalizer of P. But this last fraction is is an integer multiple of p. So this equals 1 plus kp for some integer k. This shows that n sub p is congruent to 1 mod p. So n sub p is congruent to 1 mod p. Now we know that the number of Sylow p subgroups n sub p actually divides the order of g, which is p to the n times m. So if it so happens that the number of Sylow p subgroups is 1, then clearly n sub p would divide m. If the number of Sylow p subgroups does not equal 1, then n sub p is still congruent to 1 mod p. Then n sub p cannot divide p, and hence n sub p must divide the factor m, because it divides the product p to the n times m, and if it doesn't divide any of the primes p, it must therefore divide m. So if n sub p equals 1, then clearly n sub p divides m, but if n sub p does not equal 1, then it still divides m. So in either case, we have that n sub p divides m, where the order of g is p to the n times m. And this concludes Sylow's third theorem.